So we will start at fluent. We will go into the geometry. And as we can see, we have an enclosure with the inlet and the outlet. We have fins, 5 fins, flat fins with a base. Each fin is about 0.005 meters thick or 5 millimeters thick, and the fin is 5 centimeters long. So before we start, we have to delete the fins from the enclosure. So we do that by going into create boolean, and then we have to delete the target bodies, which is the enclosure, and the tool bodies, which is the fins in the enclosure. After that, we go into our mesh. As you can see, the mesh is extremely smooth with with the maximum size of 2 × 10⁻³ meters. Also, our skewness does not exceed the maximum level, which is 0.95. It is 0.897. In addition to that, the orthogonal quality minimum is 0.19052, which is greater than the minimum value of 0.1. So now we can go and check out the setup. We check that the energy equation is on. Also, we enter into the viscous. We choose K epsilon instead of inviscid. Then we click OK, we exit. We check the materials. We chose air as the fluid and aluminum as the solid. As for the boundary conditions, we chose a temperature of 100 degrees Celsius or 373 Kelvin at the base. In addition to that, the inlet velocity of the air was at 2 meters per second. Also, the air had a temperature of 20 degrees Celsius. At the outlet, no conditions were given. After that, we go to the solution initialization. We initialize the solution at the hybrid initialization. In addition to that, after the initialization is done, we go into the run calculation. We choose our number of iterations. We chose, in this case, 100 iterations. We run our calculation, and then we get this solution. This solution is displayed by going into graphics, contours, and then we check the filled option on the left side. We had to delete the auto range option because our scale was very huge. It did not show any variation. It only showed a red into orange variation, and our temperature does not change by a huge margin. It only changes by about 12 degrees. So we had to decrease the scale to between 365 Kelvin and 373 Kelvin. By doing so, we showed our contours on the fins perfectly. After that, we can check our PowerPoint. This is going to be our mission. Over here we can see we can compare the single fin to the multi-fin. Also, we have the temperature distribution versus position. As we can see, it decreases as position increases. This temperature distribution was placed on the center of the fin, that is at 0.0025 meters or 2.5 millimeters of thickness in the fin. We can check our results, and it shows that the convective coefficient from the analytical results is greater than the convective coefficient calculated numerically. Obviously, the single fin efficiency, which is 0.8356, is less than the array of fin efficiency, which is 0.8585. However, the effectiveness is for a single fin is greater than the array of fins. For instance, the single fin effectiveness is 0.9189, while the array of fins effectiveness is 0.89. This should not be the case. In addition, the calculated convective coefficient is 112.74 watts per meter squared Kelvin, while the convective coefficient calculated was from the ANSYS simulation was 120.69 watts per meter squared Kelvin. This shows the degree of error that is ignored in the ANSYS simulation. Thank you. This project was presented by Elias, Anthony Eid, and Nicole.